Hello everyone, welcome back. So in the last video we have discussed we arrive at this expression right here, AP equal PD, and now we set P is a collection of column vector alpha 1. Let me do it here. Alpha 1, alpha 2, alpha n. But we quite not sure how can we express it. So we quite not sure what's alpha. We know it's there. So in this video, we're gonna attempt to answer what is alpha. Okay. So before doing that, let me review some matrix multiplication. So this is a very good YouTube video. I think the channel is called 3 Blue 1 Brown. He did a lot of cool mathematics. He has a playlist on linear algebra. I think it's really helpful if you want to understand the intuition behind it. So I will cite some of his teaching in this video. So according to 3 Blue 1 Brown video, and the video title I think is matrix multiplication as composition. Okay, so what did he do in the video? So let's say you have 2 by 2 matrix A, B, C, D, and you want to multiply it with a 2 by 2 matrix E, F, G, H, E, F, G, H. So instead of using the formula, the intuitive way is doing this. The intuitive way you think about it is let's call this left matrix, this is right matrix. So the intuitive way of this is you think about the left matrix, right? The left matrix, they will transform each column vector of the right matrix. So this EF, EG right here, this EG right here will be transformed by ABCD. It will do something and it will become E2, G2. And similarly with F and H, they do the same transformation for F and H, and it become F2, H2. Okay, so let's express that in term mathematics, make more sense. So multiplication, this equal to, you apply the transformation A, B, C, D onto the first column vector on the right, which is EF. And you also apply the transformation ABCD on the second vector FH. Okay, like this. So how do you apply the transformation ABCD on EF? So the core definition is that E, okay, let me make a big bracket right here. So it's E right here, okay, what I'm highlighting will undergo AC transformation. So let me write like this. So it will be E, it will be undergo AC transformation, and then you can add it to F. F will undergo BD transformation. So let me use a different color so that it indicate better. So let me see, red. So okay, nice. So this is F. So F will be undergo BD transformation as highlight here, and E will be undergo the AC transformation. Okay, and then you add them up, so you get a new column vector. So EAC plus FBD. And similarly for the second one, you get FAC plus HBD. Okay, so you get EA plus FB, and you get EC plus FD. Okay, similarly with this, you get FA plus HB, FC plus HD. Okay, so EA plus FB, EC plus FD is your new EG. So you see, originally it's just EG, but you know, after the transformation, they wait. Actually, I think I write something wrong. EF. Oh, this is supposed to be EG. My apologize, guy. This should be EG right here. Should be a G. Let me change this. Okay, it should be a G right here. That's why it's kind of weird. No, I know this should be a G. And then you get GB here and GD here. Okay, so the video explained way better, but that's the intuition. You know, each one. So EG become EA plus GB. So E has shift something and G has shift something. Okay, so when you apply that, that's what you get. You get the completely new basis vector. Okay, so if you apply this principle presented by Tree Blue One Brown, and if you want to watch, if you want to listen to a better explanation, you can watch the video Matrix Multiplication as Composition by Tree Blue One Brown, the one and only. He's really good. Okay, so let's go ahead and label this. So we have a principle right here. So this is 1, this is 2. So you can write from 1 and 2. We'll arrive at what? So let's look at what is 1 again. You see, A is a big matrix, right? And alpha 1, alpha 2 to alpha n is a column vector, correct? It's a column vector. So based on the Tree Blue One Brown principle we have, which is 2, we already go through it. We can generalize it. And we can say A alpha 1, A alpha 2, all the way to A alpha n will be equal to, see. So the P apply for each. So you do the same for each. So you be P lambda 1, 0, 0, 0, P 0, lambda 2, 0, 0, and on the way. Okay. So there's something interesting you can notice. Okay, you have to notice something interesting. That interesting thing is this expression right here. P alpha 1, 0, 0, 0. You can actually simplify it. So you can simplify many expression on the right. So how can you simplify it? So P and the 1, 0, 0, 0, right? So what did it become? So remember, what is our P? Okay, so P, okay, let's say for example, this is a 4 by 4 matrix. Okay, so P have, so let's say in this case, you remember how I say A is an n by n matrix. So for our example, this case, you can assume A is 4 by 4. So what is our P gonna look like? Our P gonna look like alpha 1, alpha 2, alpha 4. Okay, and then you apply it to lambda 1, 0, 0, 0. Okay, so what's gonna happen is if you use the basic vector multiplication, you will get it will equal to alpha 1 lambda 1 plus alpha 2 times 0 plus alpha 3 times 0 plus alpha 4 times 0. So basically the rule is this. You times this for 1, times this, and you time this here. And you add them up. You get alpha 1 lambda 1. Okay, so this principle right here, if you apply to the rest of the matrix, you apply to the rest matrix, apply to the rest. So you should get like P0 lambda 2 0 0. It will be alpha 2 lambda 2, and P 0 0 0 lambda n will be lambda n alpha n. Okay, so I can simplify, let's call this 3. I can simplify 3. All right, I can simplify 3 to what? I can simplify 3 to let's see. Okay, I can simplify 3 to oh, okay, I got it. So A alpha 1, A alpha 2, A alpha n, all that will equal to lambda 1, alpha 1, lambda 2, alpha 2, oh, let's make it consistent. Lambda 2, alpha 2, all the way to lambda n alpha n. And if you equate the left-hand side and the right-hand side, equate left-hand side and right-hand side, so they have to be equal, right? So you can equate them. So this term right here equal to this term. This term right here equal to this term. And this term right here equal to this term. Okay? You see what I'm saying? Yellow equal yellow, green equal green, blue equal blue. Excellent. So you get A alpha 1 equal lambda 1 alpha 1, A alpha 2 equal lambda 2 alpha 2, and all the way to A alpha n equal to lambda n alpha n. Okay, so have you seen the definition? So this is exactly, if you look at this definition, this star definition right here, according to star, alpha n, or in this case a random alpha, let me put alpha I, not alpha n, so it won't be alpha I, is an eigenvector of A. Okay, wonderful, because this is exactly the definition of eigenvectors. Okay, you have the list of you have if you can transform a matrix, if you can find number alpha to transform matrix A to become a vector, right? So in this case, lambda. So this is exactly is the eigenvectors. So alpha is the eigenvector. So let me put it this way. You look at this thing, right? A alpha 1 equal to lambda 1 alpha 1. Alpha 1 is a vector, right? So if you can find vector where you apply A and you get a scale alpha 1 of that vector a scale of lambda 1 of that vector alpha 1, that is exactly the eigenvectors. Yeah. So we know that is the eigenvector, so we can also indicate that P is a collection of eigenvectors belongs to A. Okay, so now we can find P because we know P is an eigenvector, all eigenvectors of A. And that's the topic for the next video. So in the next video, we'll figure out how to find the eigenvectors of A. Okay, thank you everyone for your interest. and I will see you soon.